So for this problem, we're going to look at these molecules and determine whether they're polar or nonpolar. And to do that, first you have to draw out all the Lewis structures, figure out the dipole movement, and figure out the net dipole movement for each molecule, and that determines polarity. So we're going to start off with this molecule. Draw the Lewis structure. You have S as your central atom, 3 O's attached. Drawing Lewis structures is pretty straightforward. You have to get the total valence electrons of the molecule, and you tack them onto the outside atoms first, and then whatever you have left over you can put on your central atom. So all of these have a valence of 6, so that gives you 24 total. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you have 18, and each of these bonds is 2, so that's 19, 20, 21, 22, and 23, 24. So you used up all your valence electrons, but the sulfur still doesn't have an octet, so you have to make a double bond with one of the oxygens. In this case, I did it with this one. You could have done it with this one or this one. It does not matter. So now that you have your Lewis structure, you can look at the dipole movement, the bond dipoles, and that's determined by the electronegativity of the atoms. Oxygen has a higher electronegativity than sulfur, so it will be going this way. That's the dipole movement. We're going towards the oxygen instead, and the oxygen has a partial negative, as opposed to the sulfur, which now has a partial positive charge because the dipole movement is towards the oxygens. So the molecular geometry for this would be looks something like this. You have your sulfur, your 3 bonds with the oxygens, your dipole movements. Alright, and because they're all straight bonds and all 3 dipole movements, just one this direction, they cancel each other out, which makes this molecule nonpolar. So this one is nonpolar. Alright, so moving on to the next one. OF2, your oxygen is your central atom. F. Same thing, you have to count up all your valence electrons, and if you have any extra, put them on the central. So this has 7, 14, and the oxygen would be 20 total. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Wait, no. It's 8, 16. Oh yeah, 17, 18, 19, 20. So that's all 20 of yours. Everyone is an octet, so you're good. Now let's do the dipoles. Fluorine actually has a higher electronegativity than the oxygen. So the dipole movement is toward the fluorines. Partial negative, partial negative, partial positive. So the molecular geometry for this one looks something like this. And you have your 2 non-bonding over there. And those are the bond dipoles from earlier. And because of these 2 non-bonding, that changes the geometry, because now you have 4 domains, and now you actually do have a net dipole movement, and that's straight down, and that makes this this molecule polar. So for this next molecule, you have Be as your central atom and 2 Cl's attached to that. The valence electron, the total valence electron is 7, 14, 15, 16. So you could put those on the outsides. So now you have 8, 16. The Cl's have octet, but the B doesn't, so you have to make 2 double bonds in this case to fulfill the octet rule on all 3 of these atoms. And so next is to draw the bond dipoles. Cl is more electronegative than Be, so they'd be going this way and this way. And now you can draw the geometry. The same thing. You have one going this way, one going this way, and these two will cancel each other out, and that makes this molecule nonpolar. So nonpolar, you can put NP there. So your next one, you have CCl4. Do that. C is going to be your central. Cl, Cl, and Cl. 7 for each Cl, 7, 14, 20, 28, and then you have 4 more from your carbon, so that's 32 total. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So yeah, you got all your valence electrons plotted out. Everyone is an octet, fits the octet rule. And now you have to do the dipoles for this one. Chlorine is more electronegative than carbon, so it'd be going like that. And I actually forgot to do the partial charges for this one, but the direction in which the dipole is going has a negative charge, and the central atom in this case would have the positive charge. So do that for this one too. Negative, 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 and the carbon would have slightly positive charge. So now you could do the geometry. C, Cl, 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 you have all of these bonds cancel each other out. All these straight bonds can cancel each other out, and that makes this also non-polar. NP. So last you have O3, and in this case it doesn't matter which oxygen is a central atom. There are just 3 oxygens. 6, 12, 18 valence electrons. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You have 2 left. You gotta tack them onto the central. Now you have a valence electron drawn. 2, 4, 6. You're gonna need to make a double bond with one of these oxygens. So I'm gonna just do that one. So now you have all 18 electrons, and you have an octet for all of them. And in oxygen, so because all 3 of these are oxygen, there's no bond dipoles because they all have the same electronegativity. So you can move on and draw the molecular geometry for this. So looks kind of like this. Would be linear, but these non-bonding throw off the shape a little bit. And because of this non-bonding pair, the molecule is polar. And you can write P So, yep, you have SO3 nonpolar, OF2 polar, BeCl2 nonpolar, CCl4 nonpolar, and O3 is polar. So 2 of these are polar, 3 of these are nonpolar. That's it.